AV specialist, even adjusting. Thank you so much. There's an announced web work locale. So this tells you how to sign into web work. Could you please do this before Wednesday? Just to let me know if I got your name entered, your ID entered, and all that stuff, and if we have any trouble. So just by Wednesday, it's kind of like, let's call it, okay, let's make it a homework. Homework 0. Log into web work. Wow, web work by Wednesday. By start of class Wednesday. That's all you have to do. And then like maybe do something in there. I don't know if it registers if you're in there, so try something. You don't even have to think, right? Like just go 7, type 7 in one of the blanks or something like that, and do something. And you will be able to you'll actually be able to do something real, but you don't have to by Wednesday. It's still highly recommended. All right, so what else do I have to tell you? I think that's about it, except that I do have a YouTube page, and that video will be up there as soon as possible. I highly recommend you subscribe. If you're not already, some of the folks in here are already subscribed to my YouTube channel because they've been in my classes before. There's nothing cool that's going to happen on that channel. It's going to be recordings from class. so there's not going to be any like me doing challenges or anything like that. You know, nothing really exciting will be up there. But you'll always be able to look back and see what happened. Okay, cool, good. I hate getting all that stuff. I love getting all that stuff out of the way. I kind of hate doing it because I just want to talk about differential equations, which is like, this is one of my favorite classes, and I think I already said that. I've got 2 classes this semester that I really, really love. So this is one of them because this, I don't know, I fell in love with calc when I took calc. Like it was just like kind of one of the first things I was really good at. And so that's why I ended up being a math major. Eventually. There was like this little period of time when I was going to do something stupid, not for everybody else, but for me really stupid, like be a business person or something like that. I was going to like, does anybody know Family Ties? You kind of know. There was like this character on there, and it was like, and he was like an economist, and I thought, that sounds cool. I'm going to be an economist. That would have been just a nightmare for a guy like me. So luckily, I steered clear of that. And this ended up being like what my thesis work revolved around, differential equations. And I want to start the hour by just giving you a sense of what does that even mean? So one of my favorite mathematicians, Stephen Strogatz, said that since Newton, we've realized that the laws of physics are best described by differential equations. So this is the language of science. This is how scientists think. This is how we can take an observation about nature and turn it into a model and an equation that we can do something with. And so I'm going to give you 3 examples just right up front. Actually, maybe 4, we'll see. And to show you how this thought process works, let's start off with the simplest thing we can possibly do. It's something you've already seen. It's probably like you did this in Calc 1, which was maybe a long, long time ago. So let's just start off with simple motion. There's so many cool things you can model with differential equations. If you have a couple, you could even like model love affairs and things like that, which is really fun and crazy. You know, you set the personality types and then you watch the relationship evolve. And we may be able to do that. We'll see. That syllabus that I have outlined, I reserve the right to do cooler things that are in that syllabus, and I'll give you a heads up. I'll give you a heads up about everything. Like exams, I'll always give you at least a week's notice. You know, everything. You'll have full notice of everything. But let's just think about an object that, I don't want to break my glasses, but just this. That's simple motion. I've got an object, I toss it up, and it comes back down, which is actually crazy. Like everything in life is so amazing if you just really look at it, right? This is just unbelievable that that just comes back. Just crazy. Everything is beautiful and has endless detail to it. So simple motion. I've got some object. Here's the ground, okay, and this is like my height, x here. So x equals height in, let's see, somebody in calculus really wanted units. So how about meters? Height in meters. So I take some object and let's model what I just did there. I take this object and I hold it at, what is that, like 4 feet? Right there, 4 feet. So 3.5 meters, maybe. Sound good? I don't know. I'm not good with meters. Does this seem okay? Sure. Yeah. Just one. What's that?
It's like 1 meter about.
Oh, this is 1 meter. Yeah. Thank you. Right. 3 feet and 1 meter. Thanks. Everybody. Yeah. That's good. Good call. You busted me on that. That's perfect. So let's say 1 meter. So I launched this thing from 1 meter, and this is the ground here. It's not a time axis yet. I'm going to make it a time axis, but I'm just trying to like show the process that's happening here. And I toss this thing up, and then, you know, it starts coming back down. So let's let x of t equal the height at time t. So this is after t seconds. And we'll say that right here, this is t equals 0 seconds. So we want to understand this. The good news is we know about this thing called gravity, right? So the simplest model of this is that, wait, what's this? What does that represent? What does this represent? Anybody remember some physicists in here? Come on, help me out with this shit. What does that represent? So think calculus. First derivative. So when time is your independent variable, instead of doing this is when x is your independent variable, we use dots to indicate differentiation by t. So if that's that, what's this guy? Oh, look at that, everybody's here. Cool. So that's the second derivative. What does this represent in this physical process? If x is the position of the object, what does this represent?
The acceleration.
This one's acceleration. This one is just the rate of change of position. So this is rate of change of position right here. And so that's change in x with respect to time. Just getting some notation warmed up. Is this all making sense? Sound legit? Okay, cool. So then this is the acceleration. This is the rate of change of the rate of change of position. How fast is the velocity changing? So this is, you can also think of this as velocity, if you want. And then this is acceleration. What do I know here? I live on Earth, stuck on it. Why am I stuck on it? Gravity. Which of these things relates to gravity? Second derivative. So gravity is the acceleration. It's a rate of acceleration that represents kind of like the mass. There's this huge mass below me, right? And we have this whole thing, Newton's second law, something like that. And we know that this is like your weight, right? So this is your weight, and this is your mass. And this A here, this is gravity for us. When you weigh yourself on a scale, gravity is pulling you down toward the center of the Earth. And you have a certain mass, and this gravity contributes to your mass being pulled toward the mass of the Earth. I get scared when I start talking physics. I go, look, is this sounding okay? Is this all sounding legit? Like, I'm not a physicist. I'm a mathematician who can read physics because I know math. Okay, so everything accelerates back down toward the Earth at the same rate. And if I'm doing meters and seconds, what is this? Meters per second squared, beautiful. What is the number? 9.8. Okay, so let's hold off for a second. Now, if this is, say, x equals 0, and x is increasing as I move up this way, that acceleration is actually working against moving up this way. So if I throw this object up, gravity's pulling this way, right? Gravity's acting in this direction. And so this is a negative number right here. Just the way I've set this up. If moving up increases my distance, then gravity is acting in the other way to decrease that distance. So the only thing I really know right now is this. I know that the second derivative of x with respect to time is this number. Everything else I got to figure out. So let's start with our first differential equation. This is a differential equation. It relates the derivative of a quantity to something else. And here it's just a number. So this is a very simple diffie-q, and this is like one you do in Calc 1, right? So you've seen this before. Anytime you know the acceleration of gravity is negative 9.8, that's a differential equation. How can I move from here to the velocity? What calculus technique do I use? Integration, right? Yeah, to move from second, thank you. Wait, what did you say?
It's integration.
You said integration, yeah. Okay. All right. Yeah, okay, yeah. So yeah, I missed it all. So it's all good. So I want to integrate here with respect to time, with respect to t. I don't even have to think of it as time. And what is the antiderivative of that?
Negative 9.8x.
Or what's our independent variable here?
T.
T. It'd be beautiful. Am I done?
Plus
Plus C. Remember that stupid plus C you had to do and like you get nicked for it? It's like now it matters. So it matters in this class a lot. So I'm going to put plus C here. So and let me rewrite this. So this is actually a function of t. Let me get out of the way so Olivia can see what's going on here. What does this represent in the problem? Because if I let t equal 0, this dies, and I'm just left with this. What's like a physics phrase for this number right here? So x at 0 is our initial position. And I think Kitcher's maybe saying it. What is x dot at 0? What does x dot represent? Rate of change. It's velocity. So this is initial velocity. Awesome, cool. We're warming. It's just today's like warm up. I want this to be, chill. So this is our initial velocity. Oh wow. And so what we're going to do is instead of calling it c, we're just going to rewrite it as v sub 0. So now we have x dot at t is negative 9.8 t plus v naught, our initial velocity. How do I move from here to this expression? Integrate. That's right. So I'm going to integrate again. Can you just do that real quick for me? And then like only you will know how this turned out. Oh, I've got t these first days, I was like cashed before I came in here. Just teaching 2 classes. Exhausting. Anyone dare hazard a guess? It's not a guess, it's based upon mathematics.
Not really sure.
Vivian? Yeah?
Negative, 1/2.
Okay, so we still have this guy, so I'm cool with that. Yeah, let's get that. And then the 1/2, yeah?
And the t squared.
Beautiful.
And plus v naught times t.
Yeah.
And plus c.
Plus C. Nice. Quite perfect. And we simplify a little bit, thank you. And so then this is actually negative 4.9 t squared plus v naught t plus what? Now, thinking along these lines. X at 0 is the initial position. What do you think we could maybe just use here? Or P naught or X naught? Yeah, anything, some kind of P naught. Do I actually know that on the setup? How high was I?
1 meter.
1 meter.
Not very high, because I'm teaching. So that was 1 meter. As high as you can get off the lovely Genmaicha tea that I've been drinking all afternoon. Okay, so here, check this out. Now we have an equation of motion. That gives us how this position is going to change with respect to time. So let's say, I mean, I have to toss this thing up, right? Like, so it has to have some initial velocity. If it has 0 initial velocity, here's what happens. Okay. So I need to do something with it to get, that was pretty good. Bad catch, but good toss. So let's say I've got an initial velocity of, let's see here. No matter how I do this, there's no way in hell I'm going to be able to factor that thing with that negative 4.9. So let's just say that V naught is, I don't know, maybe we can even measure this. Yeah, okay. So maybe, it's pretty fast. So let's see, how high is it from here to there?
I'd say another meter.
Is that another meter? Okay, so,
Are we counting the seconds?
yeah, does anybody have a stopwatch? I've never done this, but I'm dying to know.
Okay.
Okay, give me a count.
Okay. 3, 2, 1. 0.35 seconds.
How much?
0.35.
Okay, cool, thank you. Okay, that actually sounds pretty reasonable. So it was 0.35 for the whole trip or to hit?
To hit.
Cool, so, okay, so 1 meter in 0.35 seconds. Can someone do this reciprocal for me? What's 1 over 0.35? That's
0.0035. No, I'm sorry.
oh, it's okay. It's okay. It's okay. It's all good. It's all good.
Not like 2.8,
2.8.
around that.
Oh yeah, that sounds good. I mean, we're clearly not going to be launching rockets with this science that I'm doing here. So this ain't rocket science. And so our initial velocity is 2.8 meters per second, and then we had a 1 meter. We don't need that, but we can put meters out here just so we know what that's all about. What is the, so like now let's actually think about this as x versus t. What is that shape? Yeah, exactly. So I just saw,
Oh, it's called a parabola?
yeah, it's cool. Yeah, whatever you call it. It was beautiful.
Oh, I went like
You
that.
got it, yeah, you went and did this. Yeah, right? It's a parabola. Does it open up or down? Better open down, right? Or something weird is going on, some sort of spacecraft with greater gravity is above us. So we have something like this. Here's our 1 meter, and what's the maximum height? How do I find that?
Isn't it 2 meters? Because
It should be. Yeah, it should. It freaking should be. But it did splat into the ceiling. It wasn't a gentle kiss. Yeah. So like this peak right here.
So you want the velocity equal
Yeah, so we take our first derivative, we set it equal to 0. We basically find when, so watch this, right? Here's maximum velocity when I release it. And it starts to slow down because gravity's pulling on it, and it gets slower and slower, and then it stops for a brief second, and then brief moment, and then comes back down. So what we want to know is when is the velocity 0, and that'll give us how long it took to get up there. So, and that'll give us this time right here of that apex. So to find the apex of this parabolic arc, set v dot of t equal to 0. And so, bless you. You're welcome. Okay, so wait, what was v prime? Oh, I got it right here. I'll just take my equation. So v dot is negative 9.8 t plus 2.8. I'm going to set that equal to 0. And so then, so set, that is a set equal to 0. So I get t equals 2.8 over 9.8. And could someone please calculate that? Looks like a 3, almost, right? It looks pretty 3-ish. Looks like a little more than 3. Or, I mean a third, sorry, I'm saying 3, I meant a third.
Yeah, 0.28.
0.28. So in a cool way, it actually kind of models what we saw. You know, it's a little off, but it's pretty damn close. How high am I there at that moment? So let's just check that out. And so x at 0.28 is going to be, I definitely need a calculator friend for this. Negative 4.9 times 0.28 squared plus 2.8 times 0.28, that's kind of neat. And plus 1. I need a friend, I definitely need a friend for this. I'm like one of these calculators is forbidden guys, but I think we're going to be using them often in here.
I got like around 1.4.
1.4?
Yeah.
Okay. Which is a little disappointing. We were hoping closer to 2, right? Like 2 meters, because we were, it seems like, but 2 meters, man, this ceiling is like 3 meters high probably, right? It ain't 2 meters. So probably this initial estimate of 1 meter being the middle of the room is way freaking off anyway. So it's all good. I just wanted to get us warmed up with some computations. How would I figure out at what time it hit ground? How would I do that? I don't want to do it, but how would I do it? I'll start clearing up while you figure that out for me. Get ready for the next example. What do I do? How do you figure out what is the height here? 0. So I set x of t equal to 0 and solve that. We ain't gonna do that, like I said. So to find the total flight time, and you'll be doing stuff like this. So this is, we're not doing this for not. Set x of t 0 itself, and that'll get it. So started with a simple idea. Gravity has an acceleration. It acts on every object. We did this from it, right? So we could take this simple differential equation and start to build up physical reality from it. Let's do another one. Is there any questions, actually? I should stop. Okay, cool, cool, cool. So I like this next one. Let's talk about radioactive decay. And let's in particular think about strontium. There's probably like all sorts of numbers like strontium 325 or something weird that goes with this. But strontium's a radioactive substance. And so that means it's constantly radiating parts of itself out into the world. It's constantly losing mass. And it has what we say is a half-life of 28.8 years. Can someone tell us what that means? What does it mean to say the half-life of strontium is 28.8 years?
Every 28.8 years it decays by half.
Yeah, so if I had 10 pounds of strontium today, in 28.8 years, I'd have 5 pounds. In 28.8 years from then, I'd have 2.5 pounds. So it's losing half of its mass equals time it takes to lose 1/2 of current mass. So let's make a little picture here. Okay, so let's say I have 100 grams of strontium today. This little cube of strontium. And I'm holding it like an idiot, like right here in my palm. And then after 28.8 years, so delta T equals 28.8, and that's in years, I've got 50 grams. And then in another 28.8 years, I've got 25.5 grams. And then let's just do one more. So this is delta T again, equals 28.8, and then another 28.8. Let's just put delta T, because that ain't changing. I've got 12.5. So let's study the rate of change in each of these instances. In this one right here, let's let M equal the mass, current mass. And in this little window right here, the change in mass over the change in time is going to be, and let's do this as a positive number, even though the mass is being lost. Well, fine, yeah, fuck it. We'll just do negative 50 grams, it doesn't matter, over 28.8 years. In this little window of time, delta M over delta T is going to be negative 25 over 28.8. And in this final little window of time, delta M over delta T is equal to 12.5 over 28.8. So notice that the rate of change, this is the rate of change in mass, is changing, right? We've got different rates of change in each of these intervals. And it actually depends completely upon how much I started with. So even though that half-life is the same, the rate of change depends on how much I have. This is simple observation. Right here, so let's just make that observation that just from this little experiment here that we totally made up, but you could do this experiment, right? Observation. The rate of change in mass is directly proportional. God, do people still use this weird little fish symbol? They do? Yeah, okay, cool, all right, cool. This just means directly proportional too. I thought that was some geezer tech there. Proportional to the current mass. If we were thinking about this on a finer scale, this delta T is freaking huge, but if I were to start thinking about smaller and smaller delta T's, this would all still hold true. It's just that half-life is really big, so that's where our observation came from. But we can note the following, that the delta M over delta T approaches M dot. In other words, dm dt, the derivative, as delta T gets closer to 0. That's just the definition of a derivative. And we shouldn't expect this phenomena to change, that the rate of change in the mass, this is the instantaneous rate of change. And that is going to be proportional to the mass still. In a way, not in the same way, not in the same numbers and all that stuff, but we can observe that dm dt is directly proportional to the current mass. Now, I want you to check that out. This is a really different equation than this last one. Remember the last one was this. Notice how this one really, it doesn't necessarily depend on t or x, right? This is a constant over here. But when we started integrating, we were using t, we were using an independent variable. Check this out, and this is where things start to get interesting. That the rate of change depends on the dependent variable. So, if I were to tell you right now, solve this for me, the thing you can't do is just integrate. That's not a way to do this anymore. I can't just say integrate both sides with respect to t, because I don't really know what m is. And let's add a little thing here. So m at 0 equals m naught. Sometimes we have this thing called an initial condition. We're going to learn today how to solve that. In fact, I'm going to give you the solution right now. Then I'll show you how to solve it in a little bit. Here, yeah. In fact, we might just get right into solving these things and eschew other examples. So, dm dt equals m, with m at 0 equals m naught. I'm just rewriting that down because I need new space, is an initial value problem. Which consists of a differential equation and an initial condition. A differential equation is any equation that relates derivatives of a function to itself. And I'm going to make that very formal in a bit. But I just want to say right now, any equation that relates derivatives of a function to itself. Here's the solution. M of t is some constant times e to the kt is a, oh, this had a k in front of it, didn't it? Yes, this k is a constant, kind of a constant of proportionality, is a solution to this first part, dm dt equals m. Let me explain why. So I've got this equation. It says to find the derivative of the mass expression, I keep forgetting that, it's just a multiple of the original expression. So this is a solution to that because if I take this equation and I find its derivative, what is the derivative of that?
C times whatever k ekt.
You're integrating, but I love that you're integrating
Oh,
like that. Yes. So what's the, yeah. So I like that you did that, but you did a lot of integration recently, so you're
Yes.
totally forgiven, yeah. How do you take the derivative of this with respect to t?
Don't you multiply it by k?
Yeah, times k. So remember this, let's do some review here really quick. The derivative of something like this is, this is the chain rule. I'm gonna use prime here. It's okay, you know what I mean? It probably feels a little homier. You just take the derivative of the exponent. So when Kitra found our answer for us, what is dm dt, she just took the derivative of the exponent on the e, and it's just k. So that pops out in front. So notice, look what we got here. dm dt is actually just k times the original function. So this is m of t. So it is literally true that the derivative of m with respect to t is just k times m itself. We're gonna do a lot of this. So like if this is like, you're kind of like, quite, it's a little vague, seems a little weird, don't worry. I'm gonna do some more examples. Actually, I'm gonna go right into some examples of what a solution is. So let's do more examples of that. We are going to focus on ordinary differential equations. These are all ordinary differential equations because they involve regular derivatives. So we will focus on ordinary differential equations. That means there's no partial derivatives. Has anybody had Calc 3 in here? Calc 3 folk, no, okay, so it's okay. And if you haven't, no, don't worry, it's not required. But if you had Calc 3, you took partial derivatives. You've got some function of multivariables, and you take derivatives with respect to the different variables. We only have one independent variable, i.e. only one independent variable. And that variable is always going to be t or x for the most part. So we're going to have something that represents a physical situation that depends on time, or just something kind of abstract that depends on x. The order of a differential equation is the order of the highest derivative. In the equation. So this first one, when I had this was second order. This one that I just came up with before, this was first order. We're gonna spend a long time on these. And then this, like the last 2/3 of the semester, we moved to second order and higher. And this is where your algebra is going to kick in and all sorts of stuff like that. But for right now, there's enough. There's a lot going on here. So let me give you some examples. I'm going to do examples of both kinds here. And let's see, and I have a couple examples worked out that I probably ought to check out my notes and see what's going on in Noteland. Okay. So I've got y prime equals 3y. Let's get on back to x's and y's. That feels good. So here's a differential equation. It is first order, and you can assume everything in here is ordinary, and there's never lurking variables. What is the independent variable here? The unspoken.
3.
Oh no, sorry, no. So like the thing that I'm taking the derivative with respect to.
Oh, why?
That's the dependent. That's our dependent.
Okay.
That's good. I appreciate you trying with me though. Do you want to try one more? What's the, so like, what is, this actually stands for what symbol?
Like dy
Or
or dt.
dx, yeah, here. Yeah, it could be t or x, and honestly, it could be t or x. I guess I was thinking, you can't read my mind. Thank God. For all of us. I was thinking of a secret x hiding in here, but you're right, it could have been a t. And it doesn't, you can't go wrong. You just pick one. But here are the independent variables x, and that's what that prime kind of, just by convention, when you see a prime, that's what this is implying. So here's a differential equation. Here's a solution. Y equals, and this is a function of x. I'm looking for a function of x whose derivative is just 3 times the original function. And so here's the solution. Because notice that y prime is, and Kitra gave us this rule. Well, that was you, right, Kitra? Yeah. Times the derivative of the exponent. And that's just e to the 3x times 3. And notice that this is just y. So that's actually just 3y right there. Whose derivative can be computed by multiplying the original thing by 3? This thing right here. There's actually infinitely many solutions. So let's just make a little note of that. I haven't given an initial condition, and when you don't have that, you will have infinitely many solutions. Actually, infinitely many solutions. And they all look like this. Kind of like what we've already seen just a little bit with that thing from before. C can be anything here, and this works. So C can be any constant. And I still have y prime equals derivative of the exponent times c e to the 3x, and this is just y. Another way to think of it is whatever function I have here, if I plug it into the equation, it makes it true. So that's another way to see this. Is there any questions on that at all? Does that make sense? Yeah, let's look at something a little more interesting. Got lots of time. Good, good, good. So, another example. I've got an equation that will become near and dear to your heart at one point. This actually models a mass spring system. This represents harmonic motion. That's not obvious now, but that will become obvious. So here's a differential equation. What's its order? Yeah, second order. So it's a second order. Ordinary, let's put a little O in front. Ordinary differential equation. I don't know, does anybody know the solution to this? That's okay. You might not need to be in here. That would be cool though. So I just thought some physicists might know or something. So here's our solution. Notice I've got dots, so t is my independent variable. Is some constant times cosine of 2t plus some other constant times sine of 2t as well. So I'm just claiming that. But let me prove that I'm not lying to you. So I claim this is a solution. And in fact, it's a general solution because it's got constants that can take on all sorts of values. I'll give you a little reading at the end of class to help you just kind of solidify a lot of this stuff. So what I need to do is find the second derivative, plug it in here, plus 4 times this original expression and show that they cancel each other out. So I'm going to compute the first derivative. Well, I mean, after you do it. Can you please find those? Let's warm up together. Chain rule, chain rule. Is that like a little seating chart thing? Did that come out? Oh, thank you. Thank you, man. I'm going to take a quick picture so I can help learn my friends. They don't know well yet. I'm not. It's cold. Give me some sanity checks along the way. Those 2's popping out because of that chain rule. Right? And if
if anybody wants me to explain any of this, please don't hesitate to ask. If you have a question, you are not the only one. I will 100% guarantee you that. I will wager dollars. Oh, I got my phone. Good guy. Take a picture in a minute. Anyone would like me to explain any of that, just like do like we're in an auction, just like you can wink, just raise a finger. You weren't raising a finger, were you, Grace? You weren't like doing some stuff. Cool, so I just, just a quick reminder, you do the outside first times the derivative inside. So, this is a solution because notice that if I take this equation and I add it to this equation here, the original. So if I take x double dot plus x, look how everything, plus 4 times x. I take 4 times this, plus 4 times x. So multiply this equation by 4, and what you get is, let's just write it all out, just to be clear. I'm going to take x double dot so this is my x double dot, and then I'm going to plus 4 times the top equation, which just becomes C1, 4C1 cos 2t, plus 4C2 sine of 2t. So this right here is 4 times x with the plus, and notice that they annihilate each other, and I've just got 0. Is that clear? Yes? So that's how I get a solution. That's not how I get it, that's why it is a solution. But that's not super fulfilling because you're not quite sure how I got that solution. I will give you a little hint. This all comes down to factoring polynomials, which is one of the great joys and amazing things in this class, that some of this stuff just becomes algebra in a way. So let's talk about finding solutions. How to find solutions. This is the first part of our class. This is literally like now begins all the stuff up to like exam 1. We're going to look at a variety of techniques for solving differential equations. And one of the hardest parts is like, what technique do I use? Kind of like with calculus, like, right? Like, how do I approach this? Or what do I do here? How do I even start? So we will study several techniques, and they only work for certain kinds of equations that apply to specific equation types. And again, the trick is going to be, what do I have? And then I just go forth and like just do the routine. The routine's pretty straightforward. So type 1 for us today, that's not an official type or anything like that, is going to be separable differential equations, DEs. So a separable differential equation the name is very descriptive of what we have here. They look like this. You have dy dx equals some function of x times another function of y. And notice that this is a product here of pure x function and pure y function, or maybe we have dx dt is a function of x times a different function of t. The key thing is I've got a product here. And what I'm going to do is the thing you always want to do in calculus. Treat this like a fraction, right? And you probably, hopefully, someone along the way told you that's not a fraction. That's notation. You can't break it apart. Today you can. It becomes a fraction starting now. So what we do is we actually separate the variables. I pull the dx over to be with the f of x, and I bring the g of y over to be with the dy. So for this one, to separate, and don't write, I mean, you can write this down now, but don't think of this as an algorithm. Just think of the idea. Separate the variables. Break the y stuff with the dy, the x stuff with the dx. So this one would kind of look like this, right? I'd have to multiply both sides by 1 over g of y, dy, and then I'd just multiply both sides by dx. And now we treat these as differentials in the way that one of the other founders of calculus came up with. So there's Leibniz. I don't know, it's probably EI. Yeah. So there's like there's two fundamental people of Western modern calculus. There's Leibniz and there's Newton. And the legend goes that Leibniz at once spelled his name with a T, like this. Leibniz, sorry. I had a German guy in class once, and he did not like me saying Leibniz. So Leibniz, he had a T in there, and he had it removed because of his rivalry with Newton. Because Newton was like our time axis guy. So like Newton came up with this idea of plotting things with respect to time. And it's really cool, right? We literally did it today. And we think of it all the time. And it also kind of fucked us up. It fucked us up to think about time as this continuous forward-moving thing. Yeah, no, I'm not sure it is. I don't know if I believe in time. Just feels like there's time, right? Yeah. So, and then it's, and then you like look in the mirror and you're like, well, you don't yet, probably. You look in the mirror, think other things. You don't think, look at how I'm decaying. I mean, I hope not. It's
That's not a me thing.
just wait. Don't, if you're doing that, stop. There's plenty of time to worry about decay of your physical vehicle. So yeah, he hated Newton's idea of time, and so he took the T out of his name because of the damn T-axis. So the legend goes. What's that?
That's fucking petty.
Yeah. It seems like, he could have. He's so worried about time, but he can't let that shit go, right? Like, that's weird. Okay, so, several Ds. I recognize I have one. Step 1 is this. Separate. Step 2, integrate. So you're going to integrate each side with respect to the variable that is written in. Now, I don't know what this g of y is, and I don't know what f is, and so this is all just kind of informal notation. Expressing a process, there's no computation that can be done with this stuff. That's it. Let's try. And I'll add one more here. Step 3. Solve for any constants of integration, or solve for the constant. You should only add one at this point. I would add the plus c. You're going to do a plus c here. I would put it on the independent variable side. And you'll get to see what I mean by this. But add plus c to the independent variable side. So if this was the t side, I would add the c to that. Solve for the constant if you have an initial condition. I'm trying so hard to not talk more about time. I'm like literally doing this so that I don't keep telling you what I want to say about time. But I have a lot to say about it. I'll just say, I recommend this book. It is one of the greatest books I ever read. It was written by a physicist, a quantum physicist, who studies time and quantum gravity, and Ravelli is the author's name. It's like one of the most spiritually compelling physics books I've ever read in my life. It broke my heart. It was beautiful. It's a beautiful book. Ravelli's a poet, not just a physicist. So let's do some examples. Okay, back on track. Come on, Timmy, you can do it. We got 10 more minutes. All right, so solve. dy dx equals x over y. Start out chilling. Yeah. Can you just do real quick? Let's warm up your algebra, because this is where things get weird for folks. The algebra. Sometimes people create algebras that don't exist in this universe. So let's warm up. Your algebra is going to get so good. Are we separating, right? Cross, multiply, yay, huzzah. Integrate now. We all feeling good about this calculus going down here? Cool, it's pretty chill, right? We're starting out super chill. Now, here's one of the other great things about differential equations. These C's are like black holes for constants. You can you can do anything to a C, you can multiply it by anything, and you can keep it as a C. Because we don't know what it is. It's fine. I'm gonna multiply through by 2, because it looks prettier. And I'm still gonna say that's C. I'm not gonna write 2C. It's just C. Wicks it up. And then, now this is fine right here, but I'm trying to understand, like in the plane, what is the locus of points that would satisfy something like this? So like for different C's, different values of C's, like let's just say C equals 1. We don't know what it is, but what if I had this equation? What are all the x, y pairs in the plane that satisfy that, that? Let's do a little tweaking. Anyone recognize this? Yeah, there's you're doing something there, Kitra. You're making,
Circle.
it's very much, if that was a plus, it would totally be a circle, and it's so related to a circle. It's like a circle turned inside out. What?
Ellipse.
It's also so related to an ellipse, but it is not. It's a hyperbola. That's a hyperbola. That is a hyperbola that opens along the y-axis, has x equals y, and x equals negative y as asymptotes, and goes like this, and it actually passes through 1 right there, and it passes through negative 1 right there, and that's cool because we're going to square that y value in. Why did I say that our friends Chris and Kitra were close? That doesn't look like a freaking circle or an ellipse. Why is that close? This is the kind of questions I ask.
If you like flip it inwards, would it meet the like semi?
Keep going. Keep saying these sweet words. Yeah.
Well, it's going outwards like that. So if you flip it inwards, like folding a piece of paper, so the centers meet, then it.
Yeah. Like, or if you took the points at infinity and you like brought them together, it's kind of like a circle that's wrapped over infinity. But here's another way to think of it that's a little more down to earth. If I took a cone, like What I mean by cone is a line rotated around a point. Yeah? Just makes it, you can see this cone. So each of these is a nape. Usually people think, that's a cone. That's not a cone, that's a nape of a cone. Nape, nape. Cones have two napes. Neck of a nape, nape of a neck, right here, right? So that's a cone. And if I intersect that cone with a plane that's parallel to the board, so it's like this axis of rotation that goes through the center here. And if I take a plane that is parallel to that central axis and slice it through the cone, so just imagine intersecting this thing with a plane and making a little slice. And then this should continue, imagine this continuing off forever. That's a hyperbola. The intersection of that plane with the cone forms a hyperbola. The asymptotes of the hyperbola are the edges of the cone. You see the slice? How do I get a circle out of this? Well, I take a plane and I intersect it perpendicular to the axis of rotation, and then I get my circle. And if it's slightly askew, I get an ellipse. So you're right here. Right there. I'm chilling on the cone. It's all good. Cool. All right, so we got time for more. Let's just flip the X and the Y. See how pretty you can make it. So here's your challenge. What does it look like, the collection of X and Y points in the plane to satisfy that? So push you even further. Solve it. Then you got it solved already? What you got? Oh yeah. Close. That plus doesn't stay a plus. So this is beautiful. This is close, but not as close as the circle was. And I walk around, I'm sorry, you going good? You are very close, except that this X comes under the X. So that's actually the X over X, do you see what I mean? So check that, think about that, yeah. It's good. It's all good, it's all good.
Thank you.
That makes sense. Oh, yeah, beautiful. Yeah, now solve for Y in terms of X. Cool. So this is dy over y. If you write it like that, it kind of, like that, so that's a natural log. Absolute value of y, natural log, absolute value. You did, so that dx should still be on top, so check that out and make sure you feel. Oh, okay, hold on. Oh, it's going. Oh, she. Yeah, that's it. Okay. Yes. That's beautiful. Yeah, it's beautiful. The only thing I would say is put the plus c on the x side because that's your independent, right? So you can, then it's easier to solve for y in terms of x. So you're actually, so this is e to that times e to the c. So this is e to the natural log of x times e to the c. Because it's a plus on the exponent, right?
Oh, because, oh, yeah.
Yeah, solid. Just gotta get that y in terms of x. Yes, yeah. Blah, blah, blah. No, this was good here. So you've already integrated, right?
Oh, yeah.
So, and then put plus c, you had a plus c, that was beautiful. So I'd scratch out the integration signs, because that's actual after the integration, put plus c. And that's good. I would actually maybe pop absolute values instead of parentheses, but that's a subtle thing.
Okay.
Yeah. Where are we at? Oh, yeah, up here. Okay, cool. So, this y, so you actually mixed variables. Notice how you got the x with the dy and the y with the dx. They got it, yeah, you just want the y with the dy and the dx with the x, yeah.
Would it just be, is that okay?
That, very close, except, so this dx would go up on top of the x, so it's actually dx over x.
Okay.
Check that out, yeah, and convince yourself that, yes. Yeah, but that plus c, that's the, so yes, that plus c goes up in the x.
Oh, does it?
That's the-
Okay.
Cool, this is a good warm-up, very good warm-up. So, see what I mean about how your algebra is gonna get good? First move, separate. X's go with the dx, y goes with the dy. I got 1 minute, I'm gonna skedaddle. Integrate. I'm using this form here. This integration form. You're gonna want an integral table. I will get you one. I got a good one. If you were in calc with me last semester, you got like the primo, but I'm gonna hook you all up with the primo stuff. I'll put it in the web, I'll put it in there tonight or tomorrow morning at the latest. So then this goes natural log absolute value y equals natural log absolute value of x plus c. Now here's the move that was getting funky. I'm going to, and Chris, you said the word multiply by e, and I'm sorry, I don't mean to point you out, but I think other people were thinking that too. I'm going to take the exponential of each side. So sometimes it really helps to think of e to the x as a function of x. It's a function of x, and like if you're a computer programmer, this is what you'd do. You'd use exp of x. So I'm going to take the exponential of both sides. Notice that the c comes up with it. And then I'm going to do a little function. So, and then also, e to the natural log of something is that something. And I'm doing, that's why I did it, because they're inverse functions of each other, provided that something is positive. So this just becomes absolute value of y. This becomes, watch this move, and you're going to do it a lot. I'm using this property, that e to a sum is the product of those two things. You would add exponents when you multiply with common bases. And so then this, look, it sucks up the c. That's just c. Easy out there, folks. They're dying for some diffy q. So this becomes absolute value of x times c. And one of the things that's going to happen in this class is you're just going to be like, absolute schmabsolute. So, that's our equation. What do those look like? What are those? Lines. They're just lines of slope c. Now, just really quick. I won't keep you long, but I just have to say this. Now, look. What is the slope of these lines? C. If you take any xy point off one of these things, so let's say it's this line right here. Take this xy point off. If you want the tangent slope, it's just the regular slope, right? The tangent slope of this line is its regular slope. Its regular slope is just the ratio of the y coordinate to the x coordinate. Literally, right? Y over x is c, the slope of the freaking line. One last thing over here. in this thing, if I wanted to find the tangent slope at any point on this hyperbola, all I have to do is take the x-coordinate divided by the y-coordinate. That gives me the tangent slope. Yay. Alrighty, friends, there'll be more. So please check into web work. You can start on it easily now. You know exactly what needs to happen. Would love to talk about it on Wednesday. Hans, would you mind getting stopped for me, my friend?
Yes.